All right, well, let's dive into one of the most important and honestly most confusing concepts in all of physics. It's a single idea that governs literally everything, from the first moment of the universe to its very last, and maybe even the reason you and I are here to talk about it. We're talking about entropy. And to see just how tricky this idea can be, you only have to ask a really simple question. What does the Earth get from the sun? The usual answers pop up right away. Warmth, light, energy. Everyone says energy. But that common sense answer, well, it leads to a bit of a puzzle. Because here's the thing. For the Earth's temperature to stay more or less stable, so we don't all boil or freeze, it has to send the exact same amount of energy back out into space as it gets from the sun. The books have to balance. So the net energy gain for the planet is, well, it's zero. So if we're not getting any net energy, what are we getting? What is the sun's real gift to us? Well, to figure that out, we have to travel back in time, about 200 years, to a discovery that was born from the ashes of war. Let's meet Sadi Carnot. The year is 1824. France has just been defeated in the Napoleonic Wars, and Carnot, a brilliant young engineer, is watching Britain's industrial power, all driven by the steam engine, take over the world. He was convinced that if he could just figure out how to build a better, more efficient engine, he could help restore France's glory. And boy, was there room for improvement. Back then, even the very best steam engines were just incredibly wasteful. They only managed to turn about 3% of the heat from burning coal into useful work. Think about that. 97% of the energy was just lost, vanished as waste heat. Carnot had to know why. So he came up with a thought experiment, a perfect, frictionless engine. It works in a four-step loop. First, you add heat from something hot, which makes a gas expand and push a piston. Step 2, you let that gas keep expanding and cooling on its own. Now here's the crucial part. To get the piston back down and reset the engine, you have to compress the gas. And to do that, you must dump some of that heat into a cold reservoir. Finally, a last little squeeze gets the gas hot again, and you're right back where you started, ready for another cycle. And that right there is the key insight. To make the engine work continuously, to complete the cycle, you have to throw some energy away as waste heat. It's unavoidable. You simply can't turn all of the heat into useful work, which means a 100% efficient engine isn't just hard to build, it's physically impossible. This idea about engine waste turned out to be so much bigger than just engines. Decades later, a German physicist named Rudolf Clausius realized that Carnot hadn't just discovered a rule for machines. He had stumbled upon a fundamental law of the entire universe. Clausius gave this idea a name: entropy. Now, you've probably heard it described as disorder or randomness, but a much, much better way to think about it is as a measure of how spread out energy is. Concentrated energy, like hot steam, has low entropy. As that energy spreads out and cools down, its entropy increases. That's it. It's the tendency for energy to disperse. In 1865, Clausius famously summed up the first two laws of thermodynamics like this. First, the total amount of energy in the universe never changes. It's constant. And second, the total amount of entropy in the universe is always increasing. Energy is always spreading out. But that just begs a deeper question, doesn't it? Why? Why does it only go one way? I can drop a glass and it shatters, but I'll never see the shards jump back together. Why is entropy a one-way street? Well, the answer, amazingly, has nothing to do with some mysterious force. It's just a matter of probability. The reason is just statistics. Imagine you have a bunch of little packets of energy that can be arranged in different ways. Is it possible for most of them to bunch up on one side? Yeah, sure, that's the state on the left, a low-entropy state. But just look at the bar on the right. There are so many more ways for that energy to be spread out evenly. It's just statistically way more likely. And here's the kicker. When you scale that up from a few energy packets to the trillions upon trillions of atoms in, say, an ice cube melting in your hand, the odds become absolutely astronomical. It's not that the energy can't flow from your cold drink back into the warm ice cube. It's just so mind-bogglingly, laughably improbable that it will never, ever happen. The universe just moves from less probable states to more probable states. That's all the second law is. Which brings us all the way back to our original puzzle. If the entire universe is constantly moving towards more probable, more spread out, higher entropy states, how in the world can you get something as ordered and complex as a tree or a human being? And what does any of this have to do with the sun? And here is the beautiful solution. The gift the Earth gets from the sun isn't just energy, it's the quality of that energy. The sun sends us highly concentrated, neatly packaged, low-entropy sunlight. This is useful, high-grade energy, completely different from the messy, spread-out, high-entropy heat that the Earth radiates back into space.
Just look at this ratio. It's absolutely incredible. For every one high-quality, low-entropy photon that arrives from the sun, the Earth spits back out about 20 low-quality, high-entropy photons. The total energy in and out is the same, but the total entropy of the universe has gone way up. And the gap between the two? Well, that's what powers everything. Every breeze, every wave, every thought you've ever had.
This leads to a truly profound, almost poetic idea. Life doesn't fight entropy. Life is a consequence of entropy. Living things are these incredibly sophisticated systems for taking in concentrated low-entropy energy from the sun or from the food we eat, using it to build and maintain ourselves, and then releasing it as disorganized high-entropy waste heat. In a way, life is one of the most elegant and spectacular processes the universe has come up with for making entropy increase. And this one-way flow, this constant spreading of energy, has the most fundamental implication of all. It's the reason we experience time itself. It gives us the arrow of time, pointing from the past to the future. The entire history of the cosmos is one long story of increasing entropy. It all began in the Big Bang, a state of incredibly low entropy, a hot, uniform soup that was, statistically, a highly unlikely arrangement. Ever since, as the universe has expanded, that energy has been spreading out, clumping into galaxies and stars, and eventually creating us. And it will all keep going until it reaches a final state of maximum entropy, the heat death, where everything is so evenly spread out that nothing interesting can ever happen again. So why do you remember yesterday, but not tomorrow? It's because the past is the direction of lower entropy. Your brain, your memories, the very feeling of time flowing forward is a direct consequence of the second law of thermodynamics. It is the universe's unstoppable journey from an improbable beginning to a much more probable end. Now, I know that sounds a little bleak, this inevitable slide into a boring, featureless universe, but think of it like this: pouring milk into a cup of tea. The beginning state, milk on one side, tea on the other. It's simple, it's ordered. The final state, when it's all completely mixed together, is also simple and uniform. But the beautiful, intricate swirls and patterns, the interesting part, that only happens in the middle during the process of mixing. Perfect order is simple. Total chaos is simple. All the complexity, all the structure, all of life itself exists in that dynamic, fleeting, beautiful moment in between. We live in the swirl, and what a fantastic place to be.
If you enjoyed this deep dive into the engine of reality, don't forget to subscribe to the Lifelong Learners Hub for more explainers that make the complex simple. Like this video to help others find it, and share it with someone who loves physics. Until next time, keep learning, because the more we understand the universe, the more we can make use of the low entropy we've got.